In this video, we'll see how matrices can be used for solving linear equations. On the top left of this screen, you can see three linear equations in three unknown variables, x, y, and z. And in each case, I've written the equations out so that all the variables are on the left-hand side already. This is just because it's going to make things easier for what we're doing. But of course, linear equations don't always look like that. So you might have to do some rearranging in order to get them in a nice convenient form for what we're going to do. So when we have these kind of equations, often what we'll do in the early days is to rearrange them or try to substitute them back into each other to try to figure out what those three variables are. Now it turns out that gets really tricky and messy if you have quite a lot of equations and lots of variables, and also in some cases it doesn't even really work. So what we can actually do is try to move to a matrix form and write these equations out in terms of matrices and vectors, and it allows us to do a lot more powerful things. It also makes the manipulation of the equations a little bit simpler when we're trying to figure out how to get our solutions. So what I've got on the right hand side here is a matrix version of these three equations. So it's an equivalent representation, but in terms of matrices and vectors. So what we've got is called the coefficient matrix here, an unknown vector or solution vector, and the right hand side vector. Now these all come from the equations we've got on the left. So obviously the unknown or the solution vector is just the variables from our equations, x, y, and z. The right hand side is that set of numbers or constants from the right hand side. And that's one of the reasons why we need our equations to be written with the constants on the right and all the variable bits on the left. The final bit, and this is the one that might not be so obvious straight away, is the coefficient matrix. Now the coefficient matrix, it's constructed of all the coefficients from the left-hand side here from the variables. Now, the thing we need to do is be careful that we get them in the correct order. So the first row here in the matrix corresponds with the first equation's left-hand side, and the numbers are the coefficients of x, of y, and of z. That's a 1 in there, 1z. So 4, 2, and 1. In the same order as we have the variables in the solution vector. So for the second equation we have 3, minus 1, and 1, because we have 3 x's, minus 1y, and 1z. And then finally 1x, 1y, and minus 2 z's from the left-hand side of the third equation. So I guess to summarize this slide, we can change linear systems into matrix equations like these. Quite often you'll see that coefficient matrix referred to as A, the unknown vector as x, and the right-hand side vector as the B vector. Okay, so it turns out that we can manipulate matrices with special things called row operations. Now, I'll tell you about those in a moment. But to do that, what we would normally do is actually write this out in an even more shorthand version than it already is, called an augmented matrix. So basically we just get rid of the x, y, z vector for the moment, just remembering that it's there basically through the order of the numbers in the matrix. So this one here is called the augmented matrix. You can see A is there, vertical line, and then the B vector. Now with that, we can then apply these three operations, and these are called the elementary row operations. The first one is that we can swap any two rows we want. We can add a multiple, a constant non-zero multiple of one row to another, and we can multiply a row by any constant that we want other than 0. Now we can do as many of those as we want in whatever order we like, and the system that results, the augmented matrix that results after we do it, it won't be the same, but it will be a system which is equivalent to the original one, which of course is equivalent to the original equations. Now, the reason why we would do that is because we want to try to get this matrix towards a form where we can solve the problem. We don't. So, for example, let's just go away from that original problem. Let's imagine that we had an augmented matrix that looked like this one. Lots of zeros and some ones in the middle here. Now remember, this all comes from equations, so it can actually go back to equations. This is saying we've got 0 x's, 0 y's, and 1 z, and that's 7. So in other words, that's telling us that z is equal to 7. Similarly, no x's, 1y, and no z's is equal to 3 is just y equals 3. And of course up there, x is equal to 4. So an augmented matrix with this diagonal form, okay, is making it really easy for us to pick out what the values of our solution would be. So that's a really great augmented matrix form to get if you have it, which of course if we look back, we haven't got that, we've got a much more complex form. So slightly more difficult looking version here, not as many zeros, it's not diagonal, this is what we'd call upper triangular. Okay, in this one we've got what we would say down the bottom here, z is equal to 2. Then the second equation here in the middle, 0x plus 1y plus 1z, that's going to be equal to 4. But of course we know that z is equal to 2 now, so y is going to be equal to 4 minus z, or 4 minus 2, which is just 2. And then finally going up to the top equation, x plus y plus z is equal to 3. But we know y and z, y is equal to 2, z is equal to 2, so we have x is equal to 3 minus 2 more is going to be equal to minus 1. Okay, so if we have these nice, neat looking upper triangular or diagonal forms for our augmented matrices, all looks good and we can get some nice, fairly simple solutions for our systems. But we don't have that. So what we need to do is apply those row operations to our original augmented matrix to try to get it to look like either this diagonal or this upper triangular form, and then we can go through this back substitution procedure. So let's have a go at that now. Let's try to apply those elementary row operations to try to get the diagonal or upper triangular form. I'm going to go for the upper triangular because it takes a little bit less effort. So let's have a go at that now. I think I want to try to get this 1 in my diagonal. That'll make it easy to work with. So I'm going to swap rows 3 and rows 1. That's one of my operations. So you can see I've got that on the right hand side right here. Swapped row 1 and row 3. That's totally okay. Equivalent system to what we started with. Now next, what I'm going to do is use the fact that I've got that 1 there on the diagonal. Okay, and what I'm going to do is I'm going to multiply row 1 by minus 3 and subtract it from row 2. And that'll allow me to get a 0 in that space there, getting me towards that upper triangular form. So my next step, I'm going to add minus 3 row 1s to row 2. So row 1 will stay the same, 1, 1, minus 2 and 1. But row 3, I'm going to get 3, take away 3 row 1s, so 3 minus 3 1s, that's going to give me 0 right there. Then next I've got minus 1, take away 3 lots of that, because I'm still taking away 3 row 1s, so I'm going to end up with minus 4 in the middle there. Then I've got a 1, take away 3 lots of minus 2, so that's going to be plus 6, so that should give me 7. And then I've got 2, take away 3 lots of 1, that should give me minus 1. And then I'm going to leave the bottom row all alone. I'm going to work with that in a moment. So 4, 2, 1, and 3. Now notice here I've got the 1 in the top and a 0 below it. That's starting to look like the upper triangular form. I also want to try to get a 0 here now. So what I'm going to do is get row 3 and I'll add minus 4 lots of row 1 to it, so that I get 4 plus minus 4 will give me 0. Why don't you try and pause the video and see if you can do that one yourself right now, and pop back and see what I've got in a few seconds. Okay, so you should get the top row stays the same, the second row also stays the same. The only thing that changes is the third row, because I've added minus 4 row 1s to it. So you can see we get the 0 there, minus 2, 9, and minus 1. Notice that we are starting to see the upper triangular form here with the zeros. Now I'm quite happy to leave this minus 4 there for my upper triangular form, but I want to get this one turned into a 0. So in order to do that, I've got to use one of my 3 row operations, adding a multiple of a row, swapping 2 rows, or multiplying by a non-zero constant. And the only way I can do that is to add a multiple of this second row. I could also add a multiple of the first row, but if I did that, it would ruin my 0 here. So I don't want to do that. I want to work with the second row because there's a 0 there and it won't give me any problems. So to get 0 here, I'm not going to add just one of these. Okay, I'm going to subtract half of it, or if you like, add minus a half of that row. Okay, so let's check that out. We're going to go add minus a half of row 1 to row 2 to row 3. So again, let's take a pause, see if you can have a go at this one yourself and try to get that 0 in both of those spaces in the bottom row. Okay, so what I've ended up with is 0, a 0 like I wanted, 11 on 2, unfortunately it's a fraction, but that's okay, and minus 1 on 2 on the right there. So we've got our upper triangular form, which is great because it means my bottom equation here is telling me I've got 0 x's, 0 y's, 11 on 2 z's is equal to minus a half. So I can easily work with that to figure out what z is going to be equal to. We've got 11 on 2 z's is equal to minus a half. I can cancel those 2's from both sides, so 11 z's is equal to minus 1, and of course that's going to mean that z is equal to minus 1 on 11. See if you can go through now and try out working with equation number 2, row 2, and try to back substitute that value for z in there to get y. Okay, so your second row should tell you that minus 4y plus 7z is equal to minus 1. And we can rearrange that. We've got minus 4y is minus 1, take away 7z's, but z is minus 1 on 11. So we have minus 4y is equal to minus 1 plus 7 on 11, or minus 4 on 11. Dividing through both sides by 4 and cancelling the minus, we're going to get y is equal to 1 on 11. Now we can use both y and z to work with equation 1, or row 1 if you like, right up the top here. So up there we have x plus y minus 2z is equal to 1, or x is equal to 1 minus y, but y is 1 on 11, minus 2z's, but z is minus 1 on 11, so that's going to be plus 2 on 11. So 1 take away, or in this case plus 1 on 11 is going to give us 12 on 11 in total. So now we can see we've got all of our solution. We've got z equal to minus 1 on 11, y equal to 1 on 11, and x equal to 12 on 11. So if you like, we can take those all the way up here and just write out our solution. So we have x equals 12 on 11, y equals 1 on 11, and z is equal to minus 1 on 11. And that is the solution to the original set of equations all the way back from the first slide through the matrix equation method. Okay, so in summary, we can solve linear systems by a method which is actually called Gaussian elimination. Now, all it is what we've seen in the last few slides, converting to matrix form first, augmenting the coefficient matrix A and the right-hand side vector B, applying the row operations until we get either diagonal form or upper triangular form, and then using the back substitution method to figure out the final values for our 3 variables in this case, or however many variables you have in your system.